Most scientists in the 1890s believed the universe was a finished masterpiece, a perfect clockwork machine governed by the laws of Isaac Newton. But there was a glitch in the system, a paradox so dangerous, it threatened to shatter everything we thought we knew about reality. Newton's math said one thing, Maxwell's equation said another, and for years, the world's greatest minds simply looked the other way, treating it like a minor accounting error. But in a small patent office in Switzerland, a 26-year-old clerk was about to do the unthinkable. To solve this conflict, he realized he didn't need to fix the math. He needed to destroy our understanding of time itself. This is how Albert Einstein broke the cathedral of physics.
Historians of science, such as Gerald Holton, note that while the catching a light beam thought experiment is often framed as a moment of sudden inspiration, it actually represents a decade-long friction with the prevailing ether theory of the late 1800s. Most physicists at the time, including Nobel laureates like Hendrik Lorentz, were desperately attempting to preserve the Newtonian structure by inventing complex, invisible mechanisms to explain why Maxwell's equations seemed to defy common sense. They chose to add layers to an aging system rather than question the system's foundation. By 1902, the person who would eventually dismantle this foundation did not sit in a position of academic influence. He was a 23-year-old technical expert, third class at the Swiss Patent Office in Bern. This was not a romanticized exile, but a systemic rejection. Having irritated his professors with a refusal to defer to their authority, Albert Einstein found himself barred from the traditional corridors of European academia. He was an outsider to the institutional power of the great universities, operating instead within the heart of the Industrial Revolution's bureaucracy. His daily task was to evaluate the feasibility of patents for synchronizing clocks across vast railway networks. It was here, amidst the mundane paperwork of a world obsessed with standardizing time for commerce and empire, that the contradiction of light became more than a theoretical nuisance. It became a question of how the universe itself is governed. If the most powerful institutions of the day could not reconcile their laws of motion with their laws of light, perhaps it was not the light that was the problem, but the very definition of the second and the meter upon which their power was built. Einstein was not looking for a miracle. He was looking for the structural flaw in the blueprints of reality. It is a common misconception that Einstein's isolation was a sign of intellectual superiority alone. Modern sociological analyses of the Annus Mirabilis papers suggest that his position outside the university system may have been his greatest strategic advantage. Free from the peer review pressures of 19th century German academia, which prioritized the preservation of Newtonian prestige, Einstein was intellectually permitted to entertain a solution that his superiors would have dismissed as professional suicide. The idea that time itself is not a universal constant, but a variable dictated by the observer's position within the system. By 1900, the meritocratic promise of the European academic system had effectively closed its doors on a young Albert Einstein. His failure to secure a teaching assistantship at the Zurich Polytechnic was not merely a personal setback, it was a systemic exclusion. In the rigid hierarchy of German-speaking academia, a student's career was dictated by the patronage of senior professors. Einstein, by challenging the pedagogical methods of figures like Heinrich Weber, had rendered himself unemployable within the state-sanctioned intellectual complex. For 2 years, he existed on the periphery of the workforce, sending out frantic applications that went unanswered, while his father's business failures deepened the family's precarious social standing. This period was characterized by a profound disconnect between individual capability and institutional recognition. Historians such as Alice Calabrese point to the correspondence from this era, where Einstein's father, Hermann, wrote a desperate letter to Professor Wilhelm Ostwald, pleading for a position for his son. Ostwald never replied. However, modern historical analysis suggests this exclusion served an unintended function. It prevented Einstein from being socialized into the normal science of the day, which Thomas Kuhn described as the tendency of established institutions to suppress fundamental novelties because they are necessarily subversive to the institution's primary commitments. The resolution to this deadlock came not from a university, but from the heart of the industrial bureaucracy, the Swiss Patent Office in Bern. To the casual observer, a technical expert class 3 was a cog in the machine of Swiss precision engineering. Yet this office was the nerve center of a global technological crisis. The late 19th century was obsessed with the synchronization of time. As railway networks expanded across Europe, the lack of a unified temporal standard was more than an inconvenience. It was a threat to the logistical power of the state. Engineers were flooding the patent office with designs for electrical clock coordination. Einstein's task was to strip these complex blueprints down to their logical core. He was immersed daily in the practical mechanics of how a signal, traveling at a finite speed, could coordinate two distant points. The boredom of the patent office was, in reality, a front-row seat to the collision between classical physics and the emerging electrical world. This brings us to the structural impasse of 1905. On one side stood the Newtonian framework, which asserted that time flowed equably without relation to anything external. On the other side were Maxwell's equations, which insisted that light possessed an absolute velocity. If the laws of the universe were consistent, these two systems could not both be right. The scientific elite of the time, including Henri Poincaré and Hendrik Lorentz, were attempting to save the system by introducing local time as a mathematical fiction, a useful trick to keep the equations working without overturning the social and philosophical belief in absolute time. The debate over priority in the discovery of special relativity remains a subject of academic scrutiny. Some historians argue that Poincaré was on the verge of the same discovery. However, the distinction lies in the conceptual framework. While the established elite viewed the constancy of light as a problem to be solved through increasingly complex adjustments to Newton, Einstein took the opposite approach. He treated the constancy of light as the primary law and concluded that the traditional understanding of time was the error. This was not just a change in physics, it was a rejection of the absolute temporal authority that had governed human thought since the Enlightenment. He chose to trust the logic of the new electrical reality over the prestige of the old mechanical one. In 1905, the solution to the systemic crisis of physics arrived not through a laboratory experiment, but through a conceptual restructuring of the observer's relationship to the state of motion. To resolve the conflict between Maxwell's light and Newton's mechanics, the logic dictated a radical sacrifice. If light must remain at a constant speed for all observers, then the foundational units of the industrial world, the second and the meter, could no longer be fixed. Consider the logical blueprint of a train moving at extreme velocity. An observer on the embankment and a passenger on the train are no longer experiencing the same now. If the passenger flashes a light between two mirrors, the embankment observer sees that light travel a longer diagonal path. In a Newtonian world, the light would simply speed up to compensate. But in the reality defined by the 1905 papers, the speed of light is the only structural anchor. Therefore, for the math to hold, the passenger's time must physically slow down. Time, previously an absolute monarch of the universe, was demoted to a local variable. This conceptual leap, known as time dilation, is often misinterpreted as a psychological trick of perception. However, as noted in the analysis by physicist John Wheeler, Einstein's special relativity was an assertion of invariance. He wasn't saying everything is relative. He was saying the laws of physics are so absolute that they will warp space and time themselves to maintain their integrity. This was a transition from a universe of fixed objects to a universe of fixed relationships. By late 1905, this restructuring reached its most potent conclusion, the equivalence of mass and energy. The formula E or share MC $2 was not an isolated discovery, but a necessary byproduct of the new rules. If an object's mass increases as it approaches the speed of light, that mass must be coming from the kinetic energy of its motion. This revealed that matter is not a permanent, inert substance, but an incredibly dense form of trapped energy. It was a realization that fundamentally altered the geopolitical potential of the natural world. The atomic age was not born in a lab, but in this specific realization that the very fabric of a grain of sand contained enough latent power to level a city. However, the publication of these ideas, now known as the Annus Mirabilis papers, did not result in immediate acclaim. Instead, it was met with a period of institutional silence that lasted for months. The academic complex of 1905 was a slow-moving conservative structure. For the editors of Annalen der Physik, the leading journal of the era, The lack of citations and the absence of experimental data in Einstein's work made it a high-risk anomaly. To the established professors of Berlin and Munich, the idea that a patent clerk could render their textbooks obsolete was not an exciting prospect. It was a nuisance to be ignored. The breakthrough into the mainstream was a result of strategic intervention by Max Planck, the most powerful figure in German physics and the father of quantum theory. Historical records indicate that Planck sent an assistant, Max von Laue, to Bern to locate this Einstein. Planck recognized that if Einstein's logic was correct, it provided the unifying foundation that the German scientific empire needed to lead the 20th century. This wasn't just a validation of a genius, it was the moment an outsider was co-opted into the central power structure of science. Even with Planck's endorsement, the resistance remained significant. For years, many prominent physicists, including Nobel laureates like Philippe Lenard, viewed this new physics as too theoretical or abstract, contrasting it with proper experimental science. This friction was the first sign of a looming schism in the scientific community, one where the abstract power of mathematics began to supersede the tangible evidence of the senses, a shift that would eventually redefine the boundaries of human knowledge and military capability. By 1915, the ambition of the theoretical framework had expanded from the behavior of light to the very geometry of the universe. Einstein's general theory of relativity proposed a structural upheaval. Gravity was no longer a force acting at a distance, as Newton had theorized, but a physical curvature of space and time caused by mass. To prove this, one had to observe a phenomenon that seemed impossible under the old regime: the bending of starlight as it passed the gravitational well of the sun. The validation of this claim was not a purely scientific endeavor, it was a high-stakes geopolitical gamble. In 1919, the world was emerging from the trauma of the Great War. Science had been weaponized in the form of chemical gas and industrial slaughter. It was within this climate of fractured international relations that Arthur Eddington, a British astronomer and Quaker pacifist, organized an expedition to the island of Principe. The goal was to photograph a total solar eclipse and measure whether the stars shifted their positions according to Einstein's mathematical predictions. The stakes for the scientific establishment were absolute. If the photographs showed no deflection, the burgeoning Einsteinian movement would be exposed as a mathematical hallucination, and the Newtonian order, already deeply entwined with the national identity of British science, would be vindicated. However, the results revealed a deflection that matched the new theory. On November 7, 1919, the London Times headlined, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Almost overnight, the power to define reality shifted from the mechanical certainties of the 19th century to the relativistic complexities of the 20th. The 1919 results remain a subject of rigorous historical debate. Some modern researchers analyzing Eddington's original plates have argued that the data was too noisy and the error margins too wide to conclusively prove the theory at the time. There are suggestions that Eddington's pacifist desire to foster Anglo-German scientific reconciliation may have influenced his enthusiastic endorsement of the results. While subsequent experiments with superior technology have confirmed general relativity with extreme precision, the 1919 announcement is often viewed by sociologists of science as a socially constructed moment of triumph. A world weary of war was eager for a story of universal harmony and intellectual transcendence. As the theory gained dominance, so too did a narrative regarding its origins. The rise of Einstein the icon began to obscure the collective structural work that made his synthesis possible. The question of priority became a friction point within the scientific community. It is a matter of record that Hendrik Lorentz had already formulated the time dilation equations, and Henri Poincaré had independently postulated that no signal could travel faster than light. In the final weeks of the general theory's development, the mathematician David Hilbert actually reached the final field equations at nearly the same moment as Einstein. The debate over whether Einstein borrowed or stole ideas from Poincaré or Lorentz reflects a misunderstanding of how scientific paradigms shift. Historians like Peter Gallison argue that while others held the pieces of the puzzle, they remained committed to the ether and the Newtonian framework. They viewed their equations as mathematical corrections to an old system. Einstein's distinct contribution was not necessarily the math itself, but the willingness to abandon the old system entirely. He was the first to realize that these were not just corrections, but the properties of a new kind of space-time. The controversy over credit underscores the tension between the great man theory of history and the reality of science as a cumulative systemic process where the final synthesizer often receives the entirety of the cultural capital. This period marked the transformation of a physicist into a global political symbol. The scientific community had found a new center of gravity, but this shift also invited a darker reaction. As the 1920s progressed, the new physics became a target for rising nationalist movements in Germany, who labeled it Jewish physics, too abstract, too un-German, and too detached from the tangible, mechanical reality they sought to restore. The struggle for the universe's laws was becoming inseparable from the struggle for the soul of the modern state. The transition from theoretical abstraction to systemic reality is most visible in the infrastructure of the 21st century. We often view the reshaping of space and time as a cosmic curiosity, but it is in fact an essential utility. Every time a satellite signal connects with a smartphone, the ghost of the 1905 and 1915 papers dictates the transaction. Because satellites orbit in a weaker gravitational field and move at high velocities, their onboard atomic clocks tick faster than those on the surface. Without the corrective layers of general and special relativity, global positioning systems would accumulate kilometers of error within a single day, rendering modern logistics, aviation, and autonomous systems non-functional. Beyond the utilitarian, this shift in thought provided the mathematical permission to discover a universe far more violent and dynamic than the Newtonian clockwork. It led to the prediction of black holes, regions where the curvature of space-time becomes infinite, and the detection of gravitational waves, ripples in the very fabric of reality caused by the collision of massive objects. To ask what the world would look like without this intervention is to imagine a civilization still attempting to solve 20th century problems with 18th century tools. We would likely possess electronics, but we would lack a cohesive understanding of the macro-universe and the microscale energy that powers our sun. While Einstein is the face of this transition, historians like Thomas Kuhn emphasize that science is a series of structural shifts. Some scholars argue that if the Berne-Patent clerk had never existed, the convergence of Maxwell's electromagnetism and burgeoning quantum observations would have eventually forced another figure, perhaps Hilbert or Poincaré, to bridge the gap. Einstein did not create the laws of physics. He identified a systemic failure in the old model at a time when industrial technology was ready to exploit the new one. However, the restructuring of reality carried a dark social tax. The realization that mass is concentrated energy changed the nature of state power forever. The letter sent to President Roosevelt in 1939 was not a scientific document, but a geopolitical one, born from the fear that an authoritarian regime would be the first to weaponize the curvature of the universe. Though Einstein was excluded from the Manhattan Project due to his political leanings and perceived security risks, the shadow of his equation looms over the Cold War and the contemporary doctrine of mutually assured destruction. The gift of understanding the stars became a permanent existential threat to the planet. Einstein's later years were marked by a public struggle to contain the forces he helped unleash. In his final days, he lamented his role in the nuclear age, yet historians of science point out a deeper irony. While he sought a unified field theory to restore a sense of deterministic order to the universe, he inadvertently paved the way for the chaotic, probabilistic world of quantum mechanics, a system he spent his final decades trying to disprove. This leaves us with a fundamental tension. The decision to publish the 1905 papers was an act of intellectual liberation that dismantled an aging, rigid hierarchy of thought, but it also stripped away the safety of our ignorance. We now inhabit a universe that is mathematically precise yet humanly terrifying, where time is flexible but our survival is not. If you were in that patent office in 1905, seeing the flaws in the blueprint of reality and knowing the destructive potential that lay beneath the math, would you have remained silent? Was this discovery a triumph of the human spirit, or a long-term hazard we were not yet mature enough to manage? The debate is no longer about physics, it is about the ethics of knowing. Share your perspective in the comments. Was the cost of this truth too high? The legacy of Albert Einstein offers a profound lesson on the structural nature of truth and the responsibility of the individual within a rigid system. His journey reminds us that the greatest barriers to progress are often not a lack of data, but the institutional attachment to outdated models. Einstein's thought experiments were essentially acts of intellectual courage, the willingness to prioritize logical consistency over the comfort of established authority. However, his life also serves as a cautionary tale regarding the autonomy of knowledge. Once a fundamental truth about the universe is unearthed, such as the relationship between mass and energy, it escapes the control of its creator and becomes a tool for the existing structures of power. The lesson here is dual. For the individual, true innovation requires an outsider perspective, the ability to look at a standardized system like the clocks of Bernin and see the fundamental flaw everyone else has been trained to ignore. For society, scientific advancement is never neutral. Every leap in our understanding of reality necessitates a corresponding leap in our moral and political maturity. Ultimately, Einstein's story teaches us that while we cannot stop the expansion of human knowledge, we must be prepared to govern the consequences of the truths we demand to know.